In the last class, we learned that any vector any function for that matter, can be represented as a column vector, provided you have defined a set of orthonormal basis vectors. Now, I had hinted that the choice of basis vector is not unique. You can choose any vectors as basis vectors, and any set of functions for that matter can be basis vectors, but they need to be orthonormal. Now, suppose you have a few vectors chosen. I'll do it this way. Yeah. Suppose you have vectors chosen which are not orthonormal, something like this. Okay. Then the question is, for example, suppose there is another vector. I'm trying to do it 3D so that you can clear. So these are just some functions. That is, we are now working in vectors so that I can illustrate things in vectors. Exactly the same things will be applicable to functions. So suppose I have this vector. Sorry, I have to. Suppose this vector is the vector A. Okay. And I want to define a set of orthonormal vectors out of this set that I start with. And that can be done within a process called Gram-Schmidt orthonormalization. So first, I need to define need to normalize this given vector. So I'll define the first vector. I'll call it 1. I have to obtain it out of the given vector, and therefore I have to divide the given vector by its norm. So it is A, and we have to root it. So that is a simple way of obtaining an unit vector out of this. So this may be our unit vector 1. Now we have to do something with the vector. Say this vector, let us call it B. We need to do something in order to obtain an orthonormal vector, something like this, out of this B. We can see that if this vector, we subtract from this vector the projection onto this vector, then I get the orthonormal one, right? So orthogonal one, we have to normalize it later. So first we take a projection, which you know how to do that, the projection vector. So this is the first step. The second step is the projection vector of B on I have to take it on 1. That is simply I have to do it this way: 1, 1, and then B. So this is the norma. This is the projection operator operating on B, gives the magnitude of the projection times the vector 1, which is the projection vector. So now I have to subtract from B. So we have to get an orthogonal vector. That is, I have to subtract from the vector B this quantity, which is 1, 1 B. Okay, so after having obtained this, I get a vector in the same way. I get a vector like this. But this is not normalized. So I'll just extend it a bit so that you know that it is not normalized. So we need to normalize this. Let's call this as, sorry, let's call this as 2 prime because it is not yet normalized. And fourth step is normalize it. Sorry. So normalization step is exactly the same. So we get the vector 2, which is say something like this, unit vector in this direction, vector 2. And this vector without normalization was the 2 prime vector by normalization of this exactly the same way. So we start with 2 prime and divide it by the square root of 2 prime. Okay. And then we do exactly the same thing for the third vector, which is the vector C. Okay. So if you take the third vector, then you have to do exactly the same way, which is get some space. So your 3 prime, I'm not now illustrating because you already know the process. We have to subtract from the vector C the projection. Well, we have to subtract from the vector C the projection onto 1 as well as the projection onto 2. Then we get the orthonormal vector, orthogonal vector. So first we subtract the projection onto 1 of C, and then we subtract the projection onto 2 of C. Okay, and then again exactly the same way, 6 normalize. That way we get a set of orthonormal vectors like this. And then any vector can be expressed in terms of that. And notice in the whole process, whatever we have done, all of them can be done to functions. So it is in no way specific to the kind of vectors that you have come across. It can easily be applied to functions because all these operations are known for the functions. Okay, so this is the way of obtaining a set of orthonormal vectors starting from any set of vectors that you have, or if you are talking in terms of functions, you can obtain any set of orthonormal functions starting from any given set of functions. Great. So if this part is understood, then we'll go on. Okay. If there is no question, we can go on. Can we? Okay, let's go on. I'll delete this and okay, let me keep it for some time, but later I have to delete this. We have learned that if you have a set of orthonormal basis vectors and we have a function, say phi, and you operate that by an operator A, and you get another function, says. So this is the action of the operator A. And in quantum mechanics, all these operators, as I said, should be Hermitian operators, but there's another important demand on the kind of operators that we use, that is, they should be linear operators. So what are then the linear operators? They should be linear operators. So suppose I have an operator omega operating on a function v to give a function v prime. That is the setting. Yes. Yeah. Okay. Now the properties are that the omega operator, if it is operating on a constant times the vector, say the components, let me consider first. So omega operator is operating on a time the components of the vector v, then you can get the constant out of it, and the omega operating on the constant components of the vector. Okay. And if you know how the omega operates on the components, we also know how the omega will change the vector. That is what we have learned in the last class. The second property that we need is that if omega operates on alpha times vi and plus beta times vi, I'll say vj because it is a different, then it would be it should have a distributive property. I can take the alpha out, alpha omega operating on pi plus beta omega operating on bj. Okay. Then we need how does the omega operate on the brass? Presently we were operating on the kets. Omega operating on the brass, we have to write from the right hand side. If we write it like this, then it will be easier for you to understand. The omega is operating on alpha times the vi. I could have written this way, but essentially in case of bra, you have to think from the right. That's why I wrote it that way. That is equal to, it is, then alpha can be taken out. It is vi omega operates on that, and alpha, the number can be taken out. The number can be real or complex, it doesn't matter. The fourth property that we need is on the ket side, same distributive property, is a bracket pi on the bra, alpha is a multiplicative constant, plus pj on that beta is a multiplicative constant, close, and omega operates on that, because these are bras, so I'm operating from the right hand side, is equal to, again the distributive property will be operative, so alpha will come out, and it will be vi operating on that is omega plus beta vj on that. So these are the properties, simple properties, almost follows from common sense of the linear operators. So our operators that we consider should be linear operators and should follow these properties, and therefore we can manipulate functions, manipulate operators this way. Okay.
Sir, if
Yes.
alpha, if alpha and beta are complex, then it should be alpha star and beta star, right? When we take it out
Take it out
of, say, like,
presently you notice that this is not inside. This is just a multiplicative constant with the vi. Had it been inside, yes, you are right. I would have put a star there. So it is basically the alpha that is multiplying with this. So all that we are doing is to just take it out. It's not inside the bra.
Okay.
Okay. Uh, Now let us see. We have already learned the character and properties of this operator. This is an operator. This we have learned as the projection operator, right? And uh, so if you operate that on some phi, you get this, and then if you operate just to recapitulate, I if you operate that on some function phi, what you get is the this is the projection magnitude and times the I unit vector. So you get essentially the projection, right? And if you add all of these projections, that means in all the directions, then you get phi back. So we have obtained the result that if you sum over 1 to n, if there are n of them, I, then this is actually the identity operator. Why? Because that was seen in the last class. Because that essentially sums up all the different components, effectively giving the vector back. So it is the identity operator. Okay. Now we will call each of these as the projection operator. Let us give a symbol like this in the ith direction. So it is an operator. Okay. In the ith direction. So your identity operator is the sum of the projection operators, I is equal to 1 to n, of the projection operators. Yeah. Okay. And the pi can act on the bras also. So if we make that act on the bra, it will be v, and pi will be acting from the right hand side. So it will be v, and then it is I. This is what I've just substituted here. And this quantity takes out the, if it had been IV, then it would be the ith component. But now, since it is opposite, it will be the starred. It will be star, the first one, and then the bra in the ith direction. Okay. And pi pj, what is that? That means you get the projection along the I direction and then get the projection and the j direction. What do you get? You get, first let me write it out, I j. This quantity is the delta ij. So effectively, I have the delta ij. Every term other than the terms where I equal to j will cancel off. Effectively, what remains is the pj. Because then this can be written as the j, this can be written as the j, and then you just put them together. This pj. What it essentially means is that once, let me write it, pi, sorry, bad handwriting, need some space, projects out the part of v along I, any further application makes no difference. Okay, so these are sort of follows from common sense, but nevertheless, I needed to write this out because at some point of time later, we may have to use these expressions, and so I need. By the way, if this is an operator, if this is an operator, then obviously any operator, as you learned in the last class, is a matrix. So how do you write out that matrix? We have seen in the last class, that is a column vector. There will be zeros, and there is some place, the ith place, where it will be 1. Okay. If that is so, then your the bra will be its own row vector, and this is 1, therefore there is no conjugation, so we can write it that way. So your bra will be I 0 0 0 0 1 0 0, that kind of thing. And then when you put them together, that means this will be first this one 0 0 0 0 1 0 0, and then this one 0 0 0 0 1 0 0, which is obviously a square matrix with all the terms 0 except 1 2 3 4 5, the fifth position here there will be 1. Okay, all other terms will be 0 0 0, and this also 0. Only one term will be 1. And when you take a summation over all i's, all that happens is that all these diagonal terms get filled up by 1. Thus, you get an identity matrix. Okay, great. So these were somewhat similar material. I'll have to now get space on my board. Clean up everything. And then I have to clean up that also. So you have understood how does this particular operator look. It's a very simple looking operator, a square matrix with all zeros except only 1 1. Okay. Now, if you have operators, then we have to also understand how to make the product. Products of operators. If you want to take a product of an operator, then obviously you have to consider the jth element of the product. There's a matrix, but you have to take the. So I have a omega operator and a lambda operator put together. That means this is a product. We are inquiring what does the ijth element look like? What will be the ijth element? So we know that for any matrix, the ijth element, we have already seen in the last class that that is obtained as the uh, the operator here and j here. This is how we obtain in the last class each element of this matrix. Okay. Now you learned why we spent so much time on the projection operator and the fact that their summation gives a identity matrix, because you see here there is a operator that is well, here there is an operator that operates on j, and then the omega operates on this, and it does not make a difference if I put a I here, it remains the same, right? Now if you put the I there, then you can expand that as the I, then omega, then I will be written as some k, and then we have to sum up overall k, and then it is the this omega operator j, right? Now this is the ikth element of omega. So this is nothing but the omega I kth element, and this is the lambda kjth element, and that is summed over all k, and this you can see that this is nothing but the simple rule of the matrix multiplication. So omega operator, lambda operator product is nothing but the product of two matrices. Good. So all the usual rules of matrix operation operate in case of these kind of operators. Operators and matrices and matrix manipulation properties all apply there. And since you know the matrix manipulation rules, then you will be comfortable with what we are going to do. The one important thing that we need in quantum mechanics is the adjoint of an operator. Adjoint of an operator. See, we already know that if you have a vector v and if you have a multiplicative constant a, then we can write it as a v, in the sense that this is a vector, this is a function. In fact, this function, on that you have just multiplied a constant. So it is a vector on that we multiplied a constant, and here it is the function to which you have multiplied the constant and treated the whole thing as a vector, though both these things are the same thing. So this is a rule that you have already learned. In the bra form, it is a b will be equal to b. It has to be taken out, but now you have to be conjugated. So this is something we have learned earlier. When what goes with the vector is a constant, but suppose I now operate in place of this by a matrix, by a operator, then what happens? Okay, so I'm now considering, let me put some space. Yeah, I'm not considering a omega operator operating on the vector v. Okay, and naturally this will be omega operating on the function and the whole thing treated as a vector. Now, in case this is the ket, operating on the ket, and if it is operating on the bra, then it will be written as omega p bra. And then, see, in case of a constant, I could take it out, but then I had to put a star. Then here also I'll be able to take it out, but then I have to operate it with some other operator. So it will be I'll call it with a dagger. Now this is the adjoint of this. That means essentially we say that if we can operate on a vector by an operator omega, on a ket by an operator omega, what is the equivalent thing, equivalent operator that must operate on the bra of the same vector? So that is the adjoint of this. Okay, so this is the definition. So this is the adjoint. Of adjoint of omega. This is the definition. Okay. Now we need to find out what this matrix is. So matrix, we need to find out what this matrix is. Assuming that we know what the omega matrix is. That means if you know the omega matrix, we know the ijth element, and we are trying to find out the ijth element of the adjoint of omega. So our task then is to find out omega adjoint, its ijth element. And as usual, we can write it as I omega dagger j. Now since the well, you notice that this one operating on the definition was that this one operating on V gives this. So we'll just apply that here. What it gives is that this will become omega I, right? This. And then J will have to remain. J will remain from here. And then this, since omega is a Hermitian matrix, it can be brought to this side. So or no, what I'll do is I'll just change positions, and then if you change position, you have to put a star. So I'll change position J omega I. It will be star, right? I'm just changing position, then it will be the conjugate one, and then this I can then write as its conjugate. Now notice, we started with trying to find out the ijth element of the adjoint. What we have ended up with is the jith element of the original this matrix, original matrix, whose adjoint we are trying to find out, and then we have to conjugate. So therefore, the elements of this is the transpose conjugate this Ji is the transposition, and here is the conjugate of. Okay, this is what we compute. So adjoint is very easy to take. That if you have a matrix, you simply take the transpose conjugate of that square matrix, you get the the adjoint of that matrix. Okay. Since we have already done the product of matrices, it might be good to just quickly do what will happen to the product of adjoints. Product of adjoints. It is essentially omega lambda, the whole thing, it's adjoint. This is what we're trying to find out. We'll find that this is nothing but the multiplication of the adjoints, but in the opposite order. Let's just prove it. We take this, since it is a adjoint thing, so we operate it on a bra. So it is omega lambda operating on V. We can put them in a bracket. So it is, I'll put them in a bracket, omega lambda operating on V. If this is the this is inside the bra, and now I want to take it out, something that operates on the bra V, I have to take the adjoint. So it is the bra V, and I have the omega lambda, its adjoint. So so now now treat the lambda operating on V as a vector. Okay. So in that case, let me give some space. In that case, omega lambda, sorry, not A, capital lambda V, this thing is treated as a vector. So this is, if I write it explicitly, it is V. This whole thing is treated as a vector. And then I can take this out. So this is equal to lambda V, and this one goes out. Therefore, it will be the adjoint. Okay. Now I take this one out. Then it will be V. Now I take this one out. It will be the lambda. Since it is inside the bra, I will take it out. I have to put a adjoint. I have to put the adjoint here, and then this is also the adjoint. So you see, we started with this, and we ended up with this in the opposite sense. So that is how this is. So what we have obtained is that the lambda, omega, these operators product adjoint is nothing but the product of the adjoint, but in the opposite order. First we have to do this one and then this one. Okay, this is the result that we have obtained as the product of adjoints. Just reversing the order has to be remembered, because this might not comment with each other. Well, since we know what is an Hermitian, Hermitian is where the matrix itself and its transpose conjugate are the same. And we have now learned that the transpose conjugate gives the adjoint. Therefore, what is a Hermitian operator? We can easily see that if I have omega and its adjoint should be the same as omega itself. So that is the character of the Hermitian operator. Okay? This is something we have learned, and today we additionally learned this. There's another definition I must give at this stage, anti-Hermitian. Anti-Hermitian is, this is omega dagger is minus. Okay. So this is what we learned so far. Now we come to unitary operator, and if you have any question, you ask at this stage. Do you have any question on what I did? Today we learned what is an adjoint, and in that process we learned how to see the Hermitian as an adjoint operation. That means they're so we have got a matrix. It's you can say the adjoint is sort of its dual, its companion. The matrix itself operates on the ket, the adjoint operates on the bra. And if they're the same, then the operator is a Hermitian. Any question? Now let's get back to what we're doing. Okay, we have learned what is Hermitian, what is anti-Hermitian. We now have to learn what is unitary matrix. Unitary is very simple. If you have a matrix U, if you have a operator U, and you have its adjoint, then the product, if that gives a identity matrix, then U is unitary. Okay, it's a very simple definition, but you will find that that comes very often in our studies. Unitary matrices have sort of, I try to visualize the unitary matrix, unitary operators as something like a complex number with unity modulus, because that doesn't change the magnitude. Let's illustrate that. First, if you have the definition, this is the definition. Then we'll first use a theorem. The theorem says that unitary operators preserve the inner product. Between vectors. Vectors de actam. That means if you have the V prime as an unitary matrix operating on a vector V, and let that be V1 prime, and applied on V1 it gives V1 prime, and applied on V2 it gives V2 prime. Okay, then the V1 prime, V2 prime, this is what we are trying to find out, because the inner product, whether it's preserved or not, and V1 prime is U, for this one, operating on V2, sorry, it's not right. It will be U operating on V2, U operating on V1. Then I can take this one out, and when we take this one out, it will be V2. This will be U dagger, because I have to take from the bra side, and U V1. Sorry, this is nothing but this is identity. Therefore, there's nothing here. It is V2. Okay. Oh, sorry. It has to be 2. It has to be 1 here. Otherwise, it will be ulta. Okay. So V2 we have written as U. V2 prime we have written as U V2. V1 prime we have written as U V1, and then we have just used the property that the product of these two unitary matrices is unity, the identity operator, and therefore you see this has a certain overlap integral. All that I'm saying is that the overlap integral is preserved if you multiply both of these with a unitary matrix. Okay. So the conclusion is that the unitary operators are like rotation operators. So point is that if you have a couple of vectors like this, sorry, I'll do it with a better tool. This one and this one. Say not this. I'll just put arbitrary directions. Okay. So this one is your V. Sorry, I'm not here. This is say V1, and this is say V2. Then the unitary operator essentially rotates both of them. This presently there is a projection. It is this much is the projection, but if you rotate both of them like this, say this one is rotated to this, and this one is rotated to the angle was not 90 degrees, therefore I have to do it carefully. Yeah. So this one is rotated to this. Sorry, I have to. Basically, this one has come here by application of this unitary matrix, and this one has come here, and now its projection remains the same. So effectively, the action of unitary operators is to rotate vectors. Okay. This is easy to visualize if you visualize vectors, but it is not easy to visualize when you actually are working in terms of functions, but it has the same effect. That means if you have a function and another function, you can always find the overlap integral between them and then apply an unitary operator on this function as well as that function. What you get, you take an overlap integral, you get the same thing. It is in your mind's eye, that should be like rotating vectors. Okay. Do we have time? Slight amount of time is there. That's okay. I'll just erase some part and so that we can finish at least the unitary operator. We have already seen that. This another theorem we'll do before we finish today. If one treats the columns of an n cross n matrix, unitary matrix, as components of a vector, of n vectors, these vectors are orthonormal. Let's prove. Let's do that a bit quickly. So we know that U dagger U is the identity matrix. So we start with I identity matrix here, J, which we know the identity matrix is only the diagonal is there. Therefore, this is nothing but the delta Ij. Okay, the elements will be like this. Now I know what this is. This is nothing but the product of the unitaries. Dagger U J, right? And this is equal to, I can now put here the identity matrix again. It will make no difference, but now I can break that identity matrix into I U K K. This has to be summed up over K U J. Do you see how we are using the fact that these summed up gives I? Wherever there was nothing, we simply put I because that makes no difference, and that allows us to extract meaningful conclusions. So this is equal to summed over K. What is summed over K? This is, sorry, this is the, this was, yeah, the first one was the adjoint. Then it will be the U adjoints I kth element, and this one is U's. These are vectors. Kjth element. Now, what does it mean? What does it imply? It implies that exactly what we have written. The K for any particular value of K, for example, we consider K is equal to 1, then this is a column, this is a column. Their behavior is such that the product gives delta Ij, that is essentially these two column vectors are mutually orthonormal. So the character of the unitary matrix is that these columns, this is a column and this is another column. These two, this column and this column can be individually considered as vectors, and these two vectors will be mutually orthonormal. That's another property that is there. Okay, we'll stop today. Now, if there is a quick question we can answer, otherwise we'll stop today. There is no time. Any question? Did you have any difficulty in solving last week's tutorial problem? Nobody reported any problem, so therefore I assume that these were easy. So we are slowly trying to get ourselves accustomed to manipulating bras and cats and treating these as vectors, functions as vectors. Now, this week we'll also again do tutorials of that type. Okay. Shall we end today?
So, just a suggestion. A lot of us are trying to learn how to write in LaTeX. So, if you could give us like one day more to submit our assignments, because most of our assignments are ready on paper, but since we're new to LaTeX, it takes a lot of time for us to write in LaTeX.
Okay. It's not all that necessary. You can always write on a piece of paper, take pictures, put it in a PDF file, done. No problem with it. Yeah, no problem at all. But at this stage, it might be good for you to learn LaTeX. If we have some time, then I'll maybe give you some preliminary introduction into writing in LaTeX. But that will take some time out of this course. So don't be so much caught up by the conversion into LaTeX. Just write on a piece of paper, take pictures, submit. No problem.
Okay, sir. Thank you, sir.
Okay. All right, let's finish, huh? So let me stop recording.